Okay, so let's implement the next sequence, which is the Knuth sequence. It has been invented by Donald Knuth, one of the greatest computer scientists ever, and it reads 1, 4, 13, 40, and 121. Now, it is not as obvious in terms of, being able to already see the pattern as it was with the Hibbert sequence, where you just had to add or subtract one value, and then you already saw the sequence. But here it's not as obvious. So let's read up on this. And we can read up on this just by going to Wikipedia. This is the article on shell sort on Wikipedia. And if we scroll down a little, we come to this, or we arrive at this part of the Wikipedia article that's called gap sequences. And here we see a bunch of different sequences. For example, the shell sequence. And here we can see it's defined as n over 2, n over 4, and so on until we reach 1. We can also see that there's the Hibbert sequence, which reads 1, 3, 7, 15, 31, and so on. And so these are the ones that we already implemented. There's the Popernov and Stasevich sequence. And now we're going to have a look at the one by Knuth. And on the left here, we can see a pretty neat equation for each of these different sequences, which just, crams all of the ideas into one little formula, one equation, and then we just have to implement this little equation here. And here, that equation is 3 to the power of k minus 1 divided by 2. And k, in our case, is just I, which is this index that is increasing with every iteration of the while loop. So yeah, knowing that it's going to be this little equation here, this shouldn't be too hard. So let's go back up here, implement this equation, and see whether we can produce these values. 1, 4, 13, 40, 121, and so on. So I'm going to go down here. I'm going to delete this. And now I'm just really going to copy paste from what we had before. I'm going to exchange this name here. And now we'll just have to update this equation here. So, oops, not like this. Just like that. And now we'll have to insert this equation, 3 to the power of I, not k. Remember, here we are using I, minus 1 divided by 2. And I'm again using this double division operator for the reasons explained before. And let's see whether that works. So I'm just going to type print Knuth gaps. I'm going to set this to 200. I'm going to run this, and voila, there's a result. So let's compare this with what it's supposed to be. 1, 1, 4, 4, 13, 13, 40, 40, 121, 121. This appears to be working. Congratulations to ourselves. We just implemented the Knuth gaps sequence. Voila. Okay, so let's go back up. What's the next sequence? It's the Tokuda sequence. It reads 1, 4, 9, 20, 46, 103. And if you look at this, you might think, okay, this is 2 to the power of 2, and this is 3 to the power of 2, and okay, 20, no. Again, the pattern is not clearly visible, so let's head back over to Wikipedia. Okay, so I am back in the Wikipedia article. Remember, this was the Knuth sequence up here. This was shell, this was Hibbert, and so on. So Tokuda is down here, and you can see that I'm deliberately not looking at this equation up here, which looks pretty cumbersome. I'm not looking at some of the other more complicated ones as well. So I'm going to focus on this one down here. This looks pretty doable. Okay, technically this isn't too hard either, but yeah, let's just stick with this one here. Ignore these brackets for the moment. This is just a fancy way of defining when to round numbers. We're doing that obviously anyway. So yeah, it's really just 1 over 5 times, in parentheses, 9 times 9 over 4 to the power of k minus 1, which in our case is I minus 1. Remember, we are using I as an index, and then we subtract minus 4. So that shouldn't be too hard. We can just copy paste our code, and we can update the equation to this, and then we should be done, and we should have implemented the Tokuda sequence. Okay, going back up here, I'm going to go down, and I'm just going to copy paste this. I'm just going to replace Knuth with Tokuda. And now we'll have to change this equation right here. So we're going to type math, and now we have to use a ceiling function. So this bracket here, which doesn't have a bottom part, but just this top part, you can see that there's also the opposite of that. Means instead of rounding down, we now have to round up to the next integer value, and we can do that using the ceil function that is part of the math library. And we haven't imported this library, so I'm kind of inclined to put it up here because we always import stuff at the top of a script. But since this is our nice comment here, I'm just gonna put it down here. So import math, and then we can use math.ceil. And what is it that we are rounding up? Well, here comes the equation. So we now have 1 over 5 times, and now comes the inner pair of parentheses. Well, not the inner pair. Remember, this is just the ceil function. So we are now only using the first set of parentheses in a math sense of parentheses, okay? So we'll now have 9 times 9 over 4, I think it was. Let's go back down here. 9 times 9 over 4. And then we're going to raise that to the power of I minus 1. And then lastly, we'll subtract 4 from that. And let's go down here. Print Tokuda gaps 100. Let's run this. Okay, and let's compare this to up here. 1, that's right. 4 and 9. 4 and 9, then come 20, 46, 103. Perfect, this is working. We just implemented the Tokuda sequence. Okay, so let's continue with the next one, which is the Sedgewick sequence, 1, 8, 23, 77, 281, and so on. Let's go and jump into the Wikipedia article. Again, we just have to generate this sequence, we just have to copy paste this equation. So I'm going to go back up here, and I'm going to insert 4 to the power of I plus 3 times 2 to the power of I minus 1 plus 1. And then we have to add this 1 up here. So copy pasting our code. And then just going to call this Sedgewick. Now we'll have to change this equation here. Okay, so this will be 4 times, not times, but to the power of I, remember, 4 times to the power, and then we'll have to add 3 times 2 to the power of I minus 1, and then lastly, we'll have to add 1. So that should be it. Let's see whether that works. Sedgewick gaps instead of Tokuda, 281, 77, 23, and 8. 281, 77, 23, and 8. That appears to be working. But remember, it's prefixed with 1, so we just have to throw in this 1. I think we saw this before when we implemented the Popernov-Stasovich gaps. So I'm going to go down here. I'm going to run this once more. And now it reads 1, 8, 23, 77, 281. Wow, this is getting long, but I have one more, and this is a super easy one. The Ciura gaps. Let's go to Wikipedia. Ciura 2001, 1, 4, 10, and so on. And it says there is no equation. It's just unknown where it comes from. It has been derived experimentally. So yeah, this is just hard coding these values. So we're going to implement that as well in the implementation. I mean, it's so simple. We can just delete this, define a new function, Ciura gaps. Technically, we don't even have to have this n in here. I'm just going to do it to make the code consistent with what we had before. And now we're going to return a list, which just includes these numbers. So we have 11,750, 701, 301, 132, 57, 23, 10, 4, and 1. So if we type print Ciura gaps of 10, we get the sequence. And yeah, I don't know if we have to worry about this, that the sequence is too large. I mean, with 10, we would only really need 4 and 1. I don't think this will be a problem. We'll see in just a second when we are now using these gap sequences in the real shell sort code. For now, I'm going to ignore this, but with the other sequences, we had to make sure that these while loops don't run forever. Otherwise, we wouldn't terminate, our code wouldn't terminate. And yeah, here we had to take care of this here. I'm not entirely sure, but I'm going to leave it at this right now.